Hello all, myself Krishna Reddy. So here I'm going to teach electronics and device and circuits, right? Here our first chapter, semiconductor physics. So here before going to the chapter 1 semiconductor physics, let us start our discussion with what is electronics. Because today our discussion is electronics, device and circuits, right? So I start with what is electronics. Right. So electronics is nothing but to study of motion of charge carriers in a semiconductor material is called as electronics. Right. Now here electronics can be divided into two parts. Nothing but electron plus mechanics. Actually it is a combination of the two words electron plus mechanics. Here this is electron mechanics, right? What is mechanics actually? Mechanics is nothing but to study of motion of objects. Here what are the motion of objects actually? Electrons, right? Simply electronics is nothing but to study of motion of charge carriers in a semiconductor material is called as what actually? Electronics, right? The next one, electronic device. Right. See, what is electronic device actually? Electronic device is nothing but the device which is made with the semiconductor material. Right. Those devices are called as electronic devices. Example. What are the examples for electronic devices actually? Diode, transistor, and SCR. Right. These are the examples for electronic devices. Right. See, electronic devices are diode, transistor, and SCR. May I know what are the basic electrical devices actually? Basic electrical devices. The basic electrical devices are nothing but resistor, inductor, and capacitor. Right. Here, from this, what is the conclusion actually here? All electronic and the basic electrical devices can be classified into two types. One is active device and another one is passive device, right? So here what is an active device actually? Active device is nothing but the device which can access a source of energy is called as what actually? Active device, right? May I know what are the examples for active devices actually? Source of energy means all voltage and current sources, right? Now, one more definition also is there. We can also define like this. See, a device which can perform the switching operation also called as what actually? Active device, right? Now, what are the example for switching operation actually here? Transistor and SCR, right? And you have a doubt. See, diode also acts as switch. Yeah, diode also acts as switch, but it cannot perform as a switch because it does not contain third terminal. Right? The third terminal can be used for controlling purpose. That's why the diode cannot perform as switch even though it can act as switch. Okay. In case of low voltage application, the transistor can be preferred as a switch. In case of high voltage applications, the SCR can be preferred as a switch. Right. That means what we can understand, the diode is not a active device, right? It may be a passive device, right? And one more definition actually, a device which can perform the amplification also called as the active device. What are the example for amplification actually here? Transistor, right? This is about active device. Coming to passive device, right? May I know what is passive device actually? Passive is nothing but the device which can dissipate the energy is called as a passive device. Example is resistor, right? Now one more definition also is there. So a device which can store the energy also called as what actually? Passive device. What are the example for the storing elements actually here? The examples are inductor and capacitor, right? This is about active device and passive device, right? Now wrote in the points, the few important points actually. Now heading electronic. Electronic. Heading electronic. To study of motion of charge carriers. To study of motion of charge carriers in a semiconductor material. In a semiconductor material. That is, electronics equal to electron plus mechanics. Electron plus mechanics. Right. The next one, electronic device. Next heading, electronic device. The device which is made with semiconductor material. Semiconductor material. Example, diode, transistor, SCR. Right. And next heading, electrical device. Electrical device. Right on. RLC are the basic electrical device. RLC are the basic electrical device. Right. Next point. Hence, all electronic and electrical devices can be classified into two types. The first one, active device. Heading, active device. Right. Now write down, a device which can perform the switching operation. Right. Example, transistor, SCR. Right. And next one, note. Diode also acts as switch, but it cannot prefer the switch. It cannot prefer the switch because it does not contain a third terminal. The third terminal can be used for controlling purpose. Hence, diode cannot prefer the switch. Hence, diode cannot prefer the switch. Right. For low voltages, next point, for low voltages, transistor can be preferred as a switch. For high voltages, SCR can be preferred as a switch. SCR preferred as a switch. Right. Next, one more definition. A device which can act as a source of energy. Which can act as a source of energy. Right. Example, all voltage and current sources. All voltage and current sources. Right. And one more definition, write down. A device which can perform the amplification. Which can perform the amplification. Example, transistor. Right. Next heading, passive device. Right. Write down. A device which can dissipate the energy. Which can dissipate the energy. Example, resistor. Right. Next one more definition. A device which can store the energy. Which can store the energy. Example, inductor and capacitor. Right. This is about passive and active devices. Right. And the next topic, energy level splitting. In a material. Right. Actually here our electrical devices or electronic devices are made with the materials, right? That's why we want to know about how energy level is splitting in a material actually. Right. Now first of all, in any material actually, any material means the material is insulator or it may be a semiconductor or it may be a conductor. Right. The electrical characteristics depends on what actually? Electrons in the outermost orbit. Right. Electrons in the outermost orbit is called as what actually? Valence electrons. What is valency? Valency is nothing but number of electrons in the outermost orbit is called as what actually? Valence. For example, I am considering a silicon material actually. Silicon. What is the atomic number of silicon actually? 14. Okay. What is the orbital structure actually? See your 1s2, 2s2, 2p6, 3s2 and 3p2. Right. Here actually total number of electrons are what actually 14, right? So in these 14 electrons, only these electrons are responsible for the conduction. That means the electrical characteristics of any material will depends on okay, valence electrons. Valence electrons are nothing but in case of silicon 3s2 and 3p2. Like that in any material actually. Right? Next, how to draw the energy band diagram for a material? The material is insulator or semiconductor or conductor, nothing but energy level splitting in a material, right? First of all, what is energy band diagram actually? Energy band diagram is nothing but it is a plot. What it is? It is a plot of energy versus lattice spacing. Lattice spacing. Lattice spacing is nothing but distance between the two atoms is called as what actually? Lattice spacing. Right. How to draw the energy band diagram for a material? Right. Here to draw the energy band diagram for a material, I am considering a silicon actually. I am considering a silicon. Right. Here, first of all, in case of silicon material actually, the silicon atoms are uniformly arranged, and also and also uniformly arranged, and also these are arranged far apart from each other initially, right? And the electrons in the 3s orbital, because here, see, I already told na electrical characteristics are depends on 3s2 and 3p2, right? So energy band diagram also can be drawn based on which orbitals actually 3s2 and 3p2, nothing but outermost orbitals, right? Here what I'm saying, here the electrons in the 3s orbital can have the same energy, can have the same energy, and electrons in the 3p orbital can have the same energy. Same energy, right? See, if these atoms are far apart from each other, what about the interaction between the atoms actually negligible, right? If interaction between the atoms is negligible. Now here, if these atoms are brought to closer, what happens? The interaction between the atoms is increases, and also these atoms can form an electronic system, and it can obey Pauli's exclusion principle. Right. See, what is Pauli's exclusion principle actually? No two electrons in an electronic system can have same amount of energy. That means, okay, all electrons having distinct energy levels. Am I correct or not? All electrons having distinct energy levels. Here, to obey this principle, all electrons can be split into multiple energy levels. Multiple energy levels. Now, again, if these atoms are further be closer, what happens? If these atoms are further be closer, what happen actually? Okay, these multiple energy levels of an electron can form a single band. It can form a single band. At lattice spacing, this single band can be divided into two bands. It can be divided into two bands. One is upper band, another one is lower band. One is upper band, another one is lower band. Right? Now, at T equal to 0 degrees Kelvin, temperature is 0 degrees Kelvin. Okay, what happen actually? All electrons will occupy lower band only, because all electrons having low energy levels. Temperature equal to 0 means there is no thermal energy. That means all electrons having low energy levels, so it can occupy the lower band. Then it can be called as valency band. Right? Now coming to upper band actually here. So with respect to valency band, I think this upper band is empty. If upper band is empty means I think we can say this is called as what actually? Conduction band. The gap between conduction band and valency band is called as what actually? Fermion band or energy gap. Fermion band or energy gap. Right? Now, this is the way to draw the energy band diagram for any material, right? I will show it. First of all, what I told actually, I am considering a which material? Silicon, right? See, in case of silicon, all atoms are far apart from each other, and also far apart from each other means what about the interaction between the atoms, right? Interaction between the atoms is what actually negligible, right? And also the electrons in the 3s orbital can have the same energy. See, electrons in the 3s orbital can have the same energy means you can represent with a single line, having same energy, right? So it is represented with a single line. And electrons in the 3p orbital can have the same energy, so you can represent with what actually? A single line, right? Here the 3p orbital is the higher orbital. That's here I am drawing here, upper to 3s orbital. Now, if these atoms are brought to closer, what happen actually? The interaction between the atoms is increases, and also these atoms can form an electronic system, and it obeys what actually? Pauli's exclusion principle, right? To obey this principle, see, all electrons can be split into multiple energy levels. All electrons can be split into multiple energy levels, right? Next, if these atoms are further be closer, what happen actually? These multiple energy levels of an electron can form a single band. It can form a single band. Further be closer, it can form a single band, right? Right? At lattice spacing, the single band can be divided into two bands. One is upper band, another one is lower band. Right? At T equal to 0 degrees Kelvin, all electrons will occupy what actually? Lower band. So this is called as what actually? Valency band. With respect to valency band, the upper band is empty, so it is called as what actually? Conduction band, right? The gap between conduction band and valency band is nothing but energy gap or Fermion band, right? See, energy gap is nothing but what actually? The gap between the two orbitals, we can say. This is the way to draw energy band diagram for any material, not only for silicon. Any material means the material is insulator or semiconductor or conductor, right? Right. Write down. Write down the important points. Write down. Energy band diagram is a plot of. Write down. Energy band diagram is a plot of energy versus lattice spacing. Right. In bracket, lattice spacing is nothing but what? Distance between two atoms. Bracket close. Right. Next point. Consider a silicon crystal. Consider silicon crystal, comma, in this silicon atoms are far apart from each other, due to which interaction between the atoms is negligible. Interaction between the atoms is negligible. Right. Next point. The electrons in the 3s orbital can have the same energy, and electrons in the 3p orbital can have the same energy. Can have the same energy. Right. Next point. If these atoms are brought to closer, then the interaction between the atoms is increases. Interaction between the atoms is increases, and also it can form an electronic system. It can form a electronic system, and it obeys Pauli's exclusion principle. And it obeys Pauli's exclusion principle. Please underline Pauli's exclusion principle. Right. Next heading, principle. Heading, principle. Right on. No two electrons in an electronic system can have same amount of energy. Right. Now complete, underline the total principle, important. This is given in competitive exams. Right. Completed. Next. To obey this principle, right on, all electrons can be split into multiple energy levels. That means each electron can have distinct energy level. Each electron can have distinct energy level. Right? Next point. If these atoms are further be closer, then these multiple energy levels of an electron there is multiple energy levels of an electron, right, can form a single band, underline single band, right. Next point, at lattice spacing, the single band can be divided into two bands. The single band can be divided into two bands. Right. The first one upper band and the second one lower band. The first one upper band and the second one is lower band. Right. Next point. At T equal to 0 degrees Kelvin, all electrons can have low energy levels. All electrons can have low energy levels, so that it can occupy lower band. So that it is named as valency band. What it called? Valency band. Underline valency band. Right. Completed? Next point. With respect to valency band, the upper band is empty. Right. So that it is named as conduction band. Right. Please underline conduction band. Right. Next point. The gap between conduction band and valency band is called as Fermi band or energy gap. What it called? Fermi band or energy gap. Right. Please underline Fermi band or energy gap. Right. Completed? And the next, copy this diagram. How energy diagram is formed. Right. Copied? The next topic. Energy band theory. And subheading valency band. Energy band theory. Now subheading valency band. Right. So what is valency band actually? Anybody? So valency band is nothing but actually it is a band of energy levels. Which are closer to the nucleus. Right. Here the electrons in the valency band can strongly influenced by the nucleus. Why it is strongly influenced by the nucleus? Because they are very closer. Right. Such electrons are called as what actually? Such electrons are called as bounded electrons. Right. You know these bounded electrons cannot move freely even though if you apply external electric field because those are bounded. Right. This is about valency band. And the next one, conduction band. Right. Second one. What is conduction band actually? See, conduction band is nothing but, right, it is a band of energy levels, right, which are far away from the nucleus, right. This is closer to the nucleus valency band, but it is what? Far away from the nucleus, okay. The electrons in the conduction band can weakly influenced by the nucleus, right. Such a electrons are called as what actually? Free electrons. That means, see, electrons in the valence band is nothing but bounded electrons, and electrons in the conduction band is nothing but what actually? Free electrons, right? Next, another one, Fermion band. Right. See, what is Fermion band actually? Fermion band is nothing but it is also a band of energy levels which lies between conduction band and valency band. Right. Next, the probability of an electron within a Fermion band is nothing but how much? Zero. That means no electron is present in the Fermion band. If no electron is present means what about its probability value? Zero. Right. This is about energy band theory. Right. Write down the points actually. The first heading valence band, right? Write down. It is a band of energy levels. It is a band of energy levels which are closer to the nucleus. Which are closer to the nucleus. Next. The electrons in the valency band can strongly influenced by the nucleus. Can strongly influenced by the nucleus. Such a electrons are called as bounded electrons. Bounded electrons, right? Underline the bounded electrons, right? And next heading, conduction band. Conduction band, right? Write down. It is a band of energy levels which are far away from the nucleus. Which are far away from the nucleus, right? The electrons in the conduction band. Electrons in the conduction band can weakly influenced by the nucleus. Weakly influenced by the nucleus. Such a electrons are called as free electrons. Such a electrons are called as free electrons. Please underline free electrons. Right. And next heading, Fermion band. Fermion band. Right. Right on. It is a band of energy levels. It is a band of energy levels which lies between conduction band and valency band. Conduction band and valency band. Right. Next point. The probability of finding of an electron. The probability of finding of an electron within a Fermion band is 0. Within a Fermion band is 0. Right. That is no electron is present in Fermion band. That is no electron is present in Fermion band. Right. Now here I am going to draw the energy band diagram actually for any material. So this one is the conduction band and the lower one is the valency band, and we have two boundaries actually here. This is EC and EV, right? EC minus EV is nothing but what actually? EG, energy gap, right? What is EC here? This EC is nothing but, okay, the bottom energy level of what actually? Conduction band. EV is nothing but what actually? The top energy level of valency band, right? Copy? Right. And next topic, classification of materials. And next topic, classification of materials. Now put the heading. Right. Here, materials can be classified into three types. Based on what actually? Based on the energy band theory or energy gap. Right. What are those actually? Insulator, right? Conductor and semiconductor. Right. This classification is based on what actually? Based on energy gap and energy band theory. Right. The first I start with insulator. Right. See, what is insulator? Right. Insulator means the material whose energy gap is very large. Very large is nothing but it is in several electron volt. Right. We can say like this. Energy gap is greater than 4 electron volts and it more. Right. What I'm saying actually, energy gap is very large. That is in several electron volts. What is electron volt actually here? Electron volt is nothing but right. It is the smallest unit of energy. Actually, energy has different units, right? We know joules, ergs, and calories, and one more is what actually electron volt, right? Here, energy gap always expressed in terms of electron volt only because here electron volt is the smallest unit of energy. Right. Now, what is 1 electron volt actually? 1 electron volt is nothing but how many joules? 1.6 into 10 power minus 19 joules. Right. Now, coming to insulator. Here, what I'm saying insulator means very large. The energy gap is very large, right? See, due to this large energy gap actually, no electron is moving from valency band to conduction band. If no electron is moving from valency band to conduction band, then we can say conduction band is empty. If conduction band is empty, we can say the material is insulator, right? Now, what are the example for the insulators actually? The example for the insulators are nothing but wood, right? Plastic, rubber, right? Next, silicon oxide, and the costliest insulator, that is diamond. Actually, in our electronics, the useful insulator is what actually? Silicon oxide. Very, very important one actually. Right on? Right on the points? Right on the points? Right? Materials can be classified into three types. Materials can be classified into three types based on energy band theory or energy gap. Energy gap. right? That is the first one, insulator. The first one, insulator. Second one, semiconductor. Semiconductor. And third one, conductor. Third one, conductor. Right. Put the heading, the first one, insulator. The first one, insulator. Write down definition. The material whose energy gap is very large. Very large. That is in several electron volt. Several electron volt. Next, electron volt is the smallest unit of energy. Smallest unit of energy. Right? Next, 1 electron volt equal to, write down this one, 1 electron volt equal to 1.6 into 10 power minus 19 joules. 10 power minus 19 joules. Right. Next point. Due to large energy gap, due to large energy gap, the material, due to large energy gap, no electron is moving from valency band to conduction band. No electron is moving from valency band to conduction band. Right? Due to which conduction band is empty. Conduction band is empty. Completed? Hence, material acts as a insulator. Material acts as a insulator. Completed? Right. Example. Write down these examples. Wood, plastic, rubber, SiO2 and diamond. Write down. Right. Thank you. To be continued in next lecture. Right.